Hello, guys.
Hey.
How are you guys?
Hey.
Hey, Colin.
Oh, all right.
Nice to
Yep.
see you in person finally.
Yeah. Nice to see you, Evan.
So glad you guys are here.
Thank
Really,
you.
really,
Thank
really
you.
looking forward to it.
Yeah. Thanks for having us.
Of course.
That's
I
it.
just wish we
It's
could have had,
exciting.
yeah, I just wish we could have had a little more relevant topic for you guys. It's sad that we just can't have those hardware hacks. Just not this time.
Yeah. Yeah, it's interesting seeing everyone in the Slack be like, I'm good at this web stack. And I'm like, oh, well,
Okay, good.
it's not completely irrelevant, but
Hmm. Yeah, no,
yeah.
it's good. We'll see a lot of that over the next little while.
Yeah, but yeah, so I'm
I
willing
think
to talk with people. I mean, that is my background. I was a web person formerly, so
gotcha. Yeah, I've been dabbling recently. They teach us C++ here, and so
hmm.
I know a lot about that, but I couldn't tell you the first thing about web development. And so I'm actually taking
Oh
my
yeah,
first I'm taking a web systems class this semester actually, which I'm really looking forward to.
right.
And I've always been
Yeah.
interested in the hardware side. I built my own computer, so I enjoy that side of it already.
Yeah. Yeah. Yeah, right. It's because we help a lot of automotive people, right? And so
Hmm.
that's all uh, definitely more valuable in automotive to have that hardware, software knowledge
Hmm.
and
Yeah,
where
kind
they
of understand.
intersect and all of that,
Exactly.
and systems knowledge. So, but yeah, I mean some of these people might be coming up with some really cool systems, and I'm like interested because
Yeah.
like who
No,
knows, right?
I was looking at the applications coming in, and we do have a, a decent number of computer engineers as well. So we might see a
Hmm.
little bit more idea on the system side of it as well, not just this very hardcore web side of it, which
Yeah.
most hackathons inevitably end up getting because
Hmm.
it's simple for somebody who understands how to make a website to go on and make something very cool. It's a little
Yeah.
harder sometimes for somebody with like a hardware background to kind of in 36 hours put
Yeah.
something together that's super like convincing. If that makes
Yeah.
sense.
Yeah. Yeah, that's definitely very true. It's easy to make a website look convincing. uh in fact, I think the only hackathon I ever I guess took part in was one by a web application which that I think had no technical side to it really. It was
Mm-hmm.
just like, hey, here's some cool pictures of beers, like this is a fun website. um like yeah, I don't think there was a database backend. It was
Yeah,
just it looked nice and with had dynamic, sort of stuff.
yeah,
Definitely
no,
that's less so what we're interested in because
mhm.
yeah, we work with a lot of complex systems.
Yeah. No, I'm sure we'll get. I think you'll find at least enough that interest you, like enough
Yeah.
that kind of combine a full set of systems that'll be, if not exactly what you're looking for, at least kind of revealing to an extent.
Yeah, and we're trying it out too, to see what we can do, see if we
Hmm.
can keep participating in a way that's like fruitful. Uh, and yeah, and I'm like our main mentors guy, so I'll just
Hmm.
be checking through, trying to see if I can help anybody.
Yeah.
Um,
And yes, as to your question about that, if you're not getting many mentor requests, you're also free to just post like an engineering office hours. We can just come by and talk to you because it might be that people will
yeah,
want to just like talk to an engineer, just like to see what it is that you guys do or stuff like that, versus like a company rep or something like that. So you can kind of hop between both if you feel like, that's how your time is best spent.
yeah, I wasn't sure. Yeah, right. Like I definitely internalized it as like I would also just have weird office hours, and you're
Mhm.
right that it could work that way, definitely. But I will try out the mentorship stuff and
Yeah,
see
I
what
just
that's about.
don't know how many people request mentoring. It could be that more people than usual will. It could be that
Yeah,
because it's online, people will feel awkward asking for help. So we will see.
yeah,
Let me just get some messages going on here.
Cool. Is my mic and video okay?
Yep.
Everything working? Wonderful. I just got a new computer like 8 hours ago, so I haven't tested it very thoroughly.
Very nice.
Wonderful. Let's see if I can do share screen and all that as well real quick.
So the audience is very software heavy?
They tend to be very software heavy generally, yeah.
Okay, that's fine. So we can tailor according to that. That's perfectly fine. Are we talking like no hardware people at all?
There will definitely be some hardware people there. And I think you'll find like a good cross section of like people who kind of have a dabbling in both.
Okay.
But
when we say hardware, we're like talking about like mechanical engineers or like ECE?
Computer engineers, ECE.
Okay.
Most of the time. There are, some mechanicals here and there, but they're much fewer and further between.
Okay. Well, that's good to know. So James, I think I can like spend a little bit more time on the SOTIF part, and I'll fly through the earlier stuff then.
Okay.
So
that works.
All algorithm based anyways.
I can't get this on the screen I want. Oh well. Evan, are people going to join this call, or are we going to transfer to another one?
They'll join this call.
Okay. Can you set up so I can share screen?
Or yes.
Should we just send you something? Or
I'll set it up so you can share a screen. There. You are a co-host now, so that should allow you to share screens.
Perfect.
I didn't even think of that.
Looks
Sorry.
like it's working. This is why we try things early.
This is why we're in this call early.
Oh, good.
There we go.
Okay, let's see. Is that the one I want?
Yes.
It is? Okay.
Hey guys, welcome to the Invensity's Tech Talk. We'll go ahead and wait a little bit for the trickle in. But you two are the first two here. A little early still. This is something that I've been really looking forward to actually, because like I love Tesla.
Oh, cool.
Like big fan of like, I have no idea on the accuracy or like the capabilities of what they're doing. But just like the
Neither
idea,
do they, most likely.
the idea of what they're doing is very interesting to me.
You may want to leave the call if you're a big fan of Tesla.
I'm a fan of what they're doing, not necessarily of how they're doing it, or
Yeah.
any of the technical aspects. And that's why I'm here.
I'm a big fan of their stock right now. I'll tell you that.
Exactly.
No kidding.
I think it broke 2,000 yesterday.
It's something crazy. I can't even begin to imagine how lucky some of those longs
A lot of my
are.
buddies are freaking out because they work there.
Aren't they splitting it 5-1 soon or something like that?
Yeah,
I believe so.
we have 5-1 split. Same with Apple.
I heard they're that there's a conspiracy is just going to hit 2100 and stop until the split. I'll let you do the math.
Elon Musk has done weirder things.
That's true. Yeah.
I would not put it past him. Take the names of his cars, for instance.
He's probably the one buying all the stock, driving the price up right now.
So I see we have some people trickling in here.
Mm-hmm.
Slowly but surely.
Are you fine with us asking questions, trying to make it a little bit more interactive?
Oh, yeah, of course. Be my guest. Everybody who can talk, unmute themselves, have their video on, whatever they want.
Cool.
I mean, because,
I'd rather not lecture people at 7 p.m. on a Friday
yeah,
evening.
no, definitely. So, I mean, the ways would usually happen is we put everybody in a big room. It's completely up to you. You guys do it. So this is just, a different version of that same concept.
I have a few of my friends. So I went to Carnegie Mellon, and a few of my friends, like 2-3 years ago, came and did this. I think it's like an overnight thing, and you guys like work on a product or something.
Yep.
Yeah. Okay. So I think they came and they were like they didn't have any place to sleep, so then they slept at my place in Detroit, and they were going back and forth.
That's great. So there's actually something very funny about that. We're technically not allowed to allow hackers to sleep.
Interesting.
Which is funny. So we went out to like the massive gym here. And we're not allowed to let them sleep there. However, we have to look after their health. And this event goes for 40 hours or so.
Oh my god.
So we have to weigh. So
yeah, they were gone like Friday, Saturday, and then Sunday they just came to my house to like open your door. We need to sleep.
Yep.
These guys were like freshmen when I was a senior at Carnegie. I was like, sure, I guess.
That sounds about right.
So I guess it's the same thing.
Is there like a topic that is supposed to be sort of the inspiration for the work, or?
So we kind of, it was actually very funny. We were planning on connectivity way back when we were planning this as an in-person hackathon, when everybody would come in here. And I think that's the only thing that stayed the same from, the beginning of January to now. And, it's actively stayed the same. But, we usually give them like a theme of like connectivity, and then kind of like a visual theme too. Like connectivity is like an underlying theme, and then we were going to go with space as like, kind of like a way to like design the hackathon.
Okay.
But that kind of went out. Space went out the door. Connectivity stayed. And so, that's where we tell hackers to start if they can't think of anything. If you can't think of anything, think of something that has to do with connectivity. Or just look at, the list of, prizes that we have. But, if you can get something for connectivity, you'll probably be more likely to be considered for, first, second, and third place prizes, because that's what we're going to kind of be judging on. Does this assist in connectivity, even in, ways you wouldn't originally think of? Stuff like that.
Is this run as like a student group?
Yep. So it's all students from all over the campus. So I'm from the business school. We have a lot of people from obviously the engineering school, people from LSA. We have people from the School of Design, because we have an incredible design team helping us as well. So everybody.
What year in the business school are you?
I am going into my senior year.
Oh, so you're my brother's also a senior in the business school.
Really?
Tahaj is his name.
Tahaj?
Yeah.
I don't remember off the top of my head. But
Wears a turban but doesn't look like me. Much smaller beard and much skinnier. He transferred from LSA his first year, but now he's going to senior year too.
gotcha. That actually narrows it down a lot because very few people transfer from LSNA.
Yeah, he was one of the lucky few.
So we can go and get started whenever you guys want. Whenever. I don't know if people will come in later or, halfway through. This is the first time for us as well. So we don't really know what to expect. We are recording this, so anybody who can't make it will be able to see it afterwards.
Cool. Will there be a way for us to share the presentation after? If
Yes,
people wanna look at
definitely.
it?
Yep.
Okay, cool.
So you can send it to me and I'll put it in the announcements or somewhere like that, and they can pull it up.
Perfect.
Cool. Okay, I guess we can begin. And Evan, just let us know how we're doing on time and things like that if we're going okay.
Will do. You guys have till 8 p.m., so you have more than enough time.
Perfect. Cool. So, good evening, everyone. Welcome to, or thanks for having us, I guess, at this virtual hackathon. My name is Tejas. I'm here with James and Colin. We're from Invensity. It's a tech consulting firm based actually in downtown Detroit, so not too far from Ann Arbor. Around like 45 minutes. We're in Greektown. Currently, I'm in Royal Oak. I think James, you're in Farmington.
Yep.
I don't know where Colin lives, but we're still in the Metro Detroit area. So we work on a variety of topics. We work on we're technically a tech consulting firm. James and I are kind of in the same practice, so we're going to kind of give you some introduction. We're trying to talk about self-driving cars, something I've worked on for quite some time. So before we jump into everything, I'll give a quick introduction about myself, and then I think we can let Colin and James also introduce themselves. So my name is Tejas, as I mentioned. I graduated from Carnegie Mellon, 2016. I was a material science and photography major. You don't see a lot of those, I promise you that. So I actually got into art school and I got into engineering school. And had a very interesting experience. I worked for worked for pharmaceuticals for a little bit in college. I also worked for General Electric. That was like one of my big internships. But like after that, I really wanted to like diversify my experience. Hence why I head up the consulting route. But I also joined a technology consulting company that was starting in Detroit that year. So a little bit of a gamble. I think it's paid off so far. I've enjoyed my time here. I've learned a lot. Worked on a variety of things. So you can name a bunch of self-driving cars. Talk about Uber. You can talk about Mercedes is coming out with one. I've worked with a bunch of local clients on camera systems, brake systems. I mean, you name it. The new F-150, James and I had a hand in the braking system there. So we've worked with a lot of different clients, a lot of different products. And we've done like a wide range of consulting. We do everything from like an engineer level, where we're actually doing like requirements and working on things like that, to some clients we're like implementing brand new processes. So we'll go into detail as to what we do, but just want to give a little bit of introduction for fun. I'm a big photo guy. I don't know if you can tell. That's my camera collection behind me. Everything there is like functional. I do photography more than like a hobby. It's also like kind of like a side job for me, and I spend a lot of time working on my art. So if anyone wants to change this completely to photography, I know James will probably be upset, but I'll be fine with it. Okay, I think we can let James and Colin introduce themselves.
Sweet. Tejas, as long as you're taking pictures for all of us, I think it's fine. He does all the headshots for Office too, which is really nice. So, before a year ago when he started doing it, we had all these like really terrible looking, picture on next to a brick wall, and it's like just the worst quality on like an iPhone 6 from 8 years ago, and now they're all like just gorgeous. Anyways, yeah, my name's James. I'm also at Invensity. I actually graduated from Michigan State. Don't hate me. In 2018. So been around a little bit now, almost coming up on 2 years with Invensity, and so this is my first job out of college, and I was kind of looking for something similar with Tejas, right? I really wanted to do, I knew I wanted to do something related to engineering. I knew I wanted to do something that was sort of technical, but I also didn't want to get too lost in the same details and end up just doing CAD work my whole life, or end up, just writing software. I'm not quite that kind of person. So I wanted to be able to get some experience doing a lot of different things. So I found Invensity. I wanted to get into consulting, and Invensity was the right balance between opportunity for career development for me, as well as being able to actually have a real life, not just work 100 hours a week. So I think, so far it's been awesome. I've had a wonderful opportunity to get involved with a lot of our internal work as well, not just sit down and work on safety management. While I have a little bit fewer project experiences than Tejas does, still had a lot of chances to work on things, especially in the world of brake systems. Just talking about the F-150 coming out. That's been one of the bigger projects that we've been supporting in the last year. And so that's been honestly just an awesome journey. For fun, what do I do for fun? I guess I read a lot. I play volleyball. We have an Invensity volleyball team that we play on Thursdays down in Detroit, at Detroit Shipping Company. We're going to win, so that's an important detail. And I guess my fun fact is I'm getting married at the end of next week, in a week from today. So that's been kind of consuming my life for the last 2 months or so, getting ready for that. But yeah, Colin, go for it. Colin, we can't hear you now. I don't know what happened, because we could hear you earlier.
Yeah, thank you.
Okay.
My name is Colin. I'm a consultant along with these guys at Invensity. I graduated in 2019. My background is in computer science, where I was a web developer for 2 years at university. Basically, as my senior project, I did a really cool sort of, me and my group did a really cool smart camera system that was the first time I felt like really satisfied with what I had done. It used Amazon Web Services as sort of on the back end to do like machine learning and stuff on people. And so I designed that system. And so coming out of university, I was like, well, that was like really the coolest experience I had. And so I was shopping around for jobs and something where I could use like my technical background. And come into Invensity, I was like, oh, okay, so this is where people sort of are able to look at the whole system, like sort of the broader scope. On that project, I like sort of fitted together the pieces, the web back end, the camera front end, and sort of the whole process between those things, the data system, etc. And I was like, that was really cool designing that. Here's a project or here's like a place where you sort of get to experience different projects and different different views of the sort of the work, not just from the software side, but I do have that background in software still, and I still like it. So that's who I am. So my favorite color is orange. I play the recorder, etc. That's the fun facts. All right.
Cool. Thank you, Colin. So we'll jump right in. Honestly, for us, this presentation is fun. I've given this presentation a lot of times, but it's fun when you guys kind of interact and kind of interrupt us and ask us questions. Try to stump us, try to figure out what we're actually trying to say. That makes it very interesting for us. So that's kind of how we want to like start this off. I will try to like ask a few questions and see if you guys are like following along. We're working on some pretty cool stuff. I gotta say, I mean, we've worked with pretty much all the competitors. or a few of the competitors in the area in these topics. So it's cool to see what's going on, why they're not putting these cars out, and things like that. So with that, we'll start. So where are those self-driving cars? When I say self-driving, I think everyone's seen there's like a level of self-driving that does exist. So I think everyone's seen like the lane keeping cars, right? They'll like bounce you back and forth. I think almost all cars are getting this basic like automatic emergency braking. Like if like a kid or an animal runs to the front, it'll slam on the brakes for you. I'm pretty sure every car nowadays has what's called blind spot detection, like simple features like that, right? But where's like the futuristic stuff? Like where's like the Jetsons level? Like, oh, I want to sit in a car and get taken to, you know, the restaurant down the road and then come back and sit in that and get dropped off home. Where is that? And the simple answer is it exists, and the technology actually works, and it exists out there. But somebody's not trying to take a risk, and somebody's trying to figure out why they're not, or somebody's trying to reason with themselves why we should or should not put this on the road. So we're going to kind of go through the discussion of that. We'll go through our, you know, these are kind of like our talking points. I'll talk about a few. James will talk about a few. So first question, like, why don't we have autonomous vehicles? What do we have in place today? Like, what's going on with this engineering world where we can actually work for these autonomous vehicles, and what's trying to work? What are we trying to do to make these things work? And then what's next, right? What are the next steps? Or when will we actually see a car? Or when will we be able to get into a self-driving car? So we're going to talk about these things and then kind of talk about the why this solves the challenges kind of in the world today. Again, this is our framework of our presentation. We would much rather you guys ask questions and take our conversation however you want. We'll get through the framework. That's not an issue at all. But with that, I think let's begin. So why don't we have autonomous vehicles on the road today? Does anyone have an answer to that question, just generically?
They can be really dangerous.
Very dangerous. Okay, that's one reason. What else?
You're pretty much experimenting with human lives. You're really testing it out. That's the only way to effectively test it. But
I agree. Yeah. So you're playing with human life. If any of you have gone to SF recently, there's a bunch of these just out there, up and down these hills, and I'm terrified because like even me driving up one of these SF hills is kind of interesting, but like a car that's technically has no driver. But what else? Let's talk about other things that play into factors.
There's no accountability. Sorry.
Go ahead. Whoever.
There's no accountability in situations.
Not every the infrastructure in place to be able to accommodate autonomous vehicles.
Okay, so I heard two things. I heard one was accountability and one was the infrastructure in place. Is that correct?
Yes.
Cool.
Mm-hmm.
So yes, accountability. Like who do we blame? There's always this discussion of like, if there's a dog and a cat, what does the self-driving car pick, or like a dog and a human? And then the infrastructure. I like that answer. I think people have seen how we drive in Ann Arbor and in Michigan, but you compare that driving from Detroit to like compared to like South Carolina. I grew up in Georgia, so like it's a much different driving style there. Compare that to New York City, much different style there. Compare that to Texas, where the speed limit's 85 miles an hour. I mean, you're flying. So like it's every single, let's say, operating domain, which is like kind of the technical word we use, is very different. These are all things that contribute to that. But when we get to the detail, and James can show you this next slide, is when anybody buys a car, the most important factor always, it seems like, boils down to safety, right? You don't want to buy like a X car, which is like super cool looking, super fast, and then you see, okay, it's failed all its crash ratings. Fuel efficiency obviously is a big discussion nowadays, and like quality and making sure customer service, these are all great factors. But I think everyone understands how dangerous cars can be, especially when in US you're driving at an average of like 55, 65 miles an hour. And these are big things that like play in a factor when you buy a car. Now, think about the big, I don't know if you guys have heard of these, but Ford Pinto, Toyota Prius, and then Takata airbags. These were like very, very big issues that they had with safety. And I mean, Takata airbags does not exist as an organization anymore. It tanked them so bad that they were never able to recover from this because it was like a lack of safety. So there's a reason why I guess these self-driving cars are being a little bit cautious. And so, you know, Google, Uber, Tesla, you know, they're releasing things in phases. Well, I guess Tesla in their commercial vehicle, but all these cars are releasing things in phases, but no one's going to be like, hey, I have the first fully self-driving car. There's an incentive behind that because they have to be liable for their product, which kind of comes to our next discussion, right? Which is product liability. So let's go through these definitions that we've kind of like thrown up here. So first question, who is we? I think we stands for, let's say, the engineers or the people who are doing product development, if that makes sense, right? All of you guys are kind of in computer science. At some point or another, you're going to be working for a company, hopefully, and you're going to be doing some level of product development or some kind of engineering, and you kind of become a part of that organization. And you as a company are putting out products, or if you're working in the Silicon Valley and working on apps, you're putting out data, or you're putting out certain apps in the market, and you're staying kind of liable to them. So then comes, for our purpose, what is safety? And then what is risk? And what is a hazard? What is acceptable? Who is responsible? So if you look at this graph here, risk is defined as the combination of probability and safety, and severity. So we're talking about these different thresholds, and you can see there's like the big threshold, the second threshold, the third threshold, like the smallest one. All these companies, exactly, James got it. So exactly what when a company tries to put out a product, right? Like if I release a self-driving car tomorrow, I can't be like, hey guys, this is my new self-driving car. It's 100% safe. No faults. It will have zero hazards. Nothing's going to happen. There's no way ever in the world to prove that, right? If you guys are releasing some kind of an app, there's going to be like level 1 beta, level 2 beta. You go back, debug it, go back, debug it, go back, debug it. And especially with these cars that, by the way, have like 3 or 4 or 5 intense processors like hooked in with a water-cooled system, you would assume that these things are being kind of debugged on a regular basis. So there's a level of risk that every company has to take. Now, what that risk is going to be set by either by the organization, management, engineers, whoever's kind of responsible. So that's what we kind of have to understand, is that like everyone takes certain risks, right? Even if I release, for example, you release, this is like my old hard drive that's sitting on my table here. It's like those old Toshiba hard drives. I think they had SSD back then, but they took the risk saying, hey, we're going to put this, and we're going to put it like kind of like a cheap plastic casing. If I drop this from like 5 feet, maybe it'll be fine. I drop it from 10 feet, it's probably done for, especially because it's like a mechanical hard drive, and something gets loose. But they take that risk when they release products. Similarly, in any kind of product that you develop or release, there's a level of risk. When it comes to self-driving cars, that risk is directly tied with safety. And we have to be, as a automotive company, everyone knows the markups on automotive cars are insane, and they make a bunch of money, and Ford makes this and that. Like, we get it, but the risk that they also have to take is also kind of interesting, because that's kind of what's going to be on their name, right? It's not going to be a self-driving car accidentally gets into an accident. It's going to say Ford self-driving car, Uber self-driving car, Google self-driving car. So each of these organizations kind of have to make that decision. If you go through, you go to the next slide, James, and you'll see that every car has, every corporation has their own definition, right? Honda has something, GM has something, BMW has something. There's also widespread organizations kind of like that work together and kind of set these rules, like NHTSA. These are companies that like set the rules as far as like, oh, we believe that this is how safety should be done. There's certain standards we follow. So there's a level of kind of rules and regulations that each company follows. We just have to kind of figure out what makes sense. And before you guys start thinking of like seat belts and airbags and things like that, that's not really what we're talking about. When we say product safety, we mean like durability. And we'll get into a little bit of detail. But when I say product durability, it's just how do we make sure that this car does not make a mistake, this self-driving car, right? And with that, if it does make a mistake, how do we recover from it? You know, if say a self-driving car makes a mistake on 696, this is like the highway that connects U of M and me, like you can't just pull over in the middle of that highway. That's not going to go down well for anybody. But how do you recover from these mistakes? Is it a hardware error, software error? We'll go through some details. So from here, I'll give it to James, and he'll kind of talk about what actually currently exists when it comes to what exists in safety today. Before I give it to James, does anyone have any questions? You guys do the reactions on Zoom, the thumbs up?
Is that a thing?
It's a thing. James, we're on Teams. We're behind.
Apparently. I didn't know.
Okay, cool. If anyone has any questions, just let me know. Don't worry about the reactions, but you can just cut me off. But here, I'll give it to James. Thanks, guys.
Yeah, and I think we should be able to see chat or something somewhere as well, if it's easier to type. Or yeah, whoever of us is not presenting, I'll look at chat probably. Yeah, so the big thing is, right, when we talk about, everybody has these different definitions, and that there is some level of a common agreement in terms of what is an acceptable amount of risk. And it's not, it's basically defined by, it's actually defined by this thing called an automotive safety integrity level. And basically it's like, these different levels correspond to, how many people are going to get hurt effectively, right? And to what degree are people going to die? That's a certain ASIL level. And then lower ASIL levels will be things of like, okay, somebody's going to break a leg or, potentially have to go to the hospital. And then like the lowest safety level is like the vehicle's damaged, but whatever, nobody's really in that much danger. That's a sort of a risk of property rather than a risk of life. So because there is somewhat of, that's somewhat standardized because it's a big topic and everybody wants to have some level of an agreement. We have these standards. And this is how we try to make the language that we use around safety, as well as the processes that we use around safety, to be a little bit more, standardized, right? And so the standard we're going to talk about first here is going to be ISO 26262, and it's the standard for functional safety. Now, does anybody know when I say functional safety, what the difference between that is and when we just say safety? Because it's something specific. And it's okay if not, it's not a trick question. All right, here's how you can think about it. Functional safety is basically safety of the system from particularly around like embedded electronics. It's electronic systems. So the difference between just saying safety, okay, safety of the vehicle, that's talking about crash tests. That's talking about, what's going to happen if I drive into a wall or somebody T-bones me in an intersection or something like that. That's just safety. But functional safety is really talking about what happens if I have an ECU failure? What happens if my software has an error in it that we didn't catch, and or how do we ensure that there aren't software errors that's going to cause the vehicle to behave differently than what I expect on the road? That's what functional safety is targeting. So it's not any of the mechanical things per se. It like touches on that very briefly, but really only at the point where it intersects with the electrical part of the system and the software part of the system. So I want to get that out of the way before we go deeper. Cool. So over the years, a lot of different organizations, right? We put up, NHTSA and Ford and GM and BMW and all these different companies. Safety has been on their minds, right? It's not like it's all of a sudden just today, consumers decided that safety is important, and so we're gonna think about it. It's been on the radar for a long time, and so all of these organizations have developed these different tools to evaluate the system safety. And so these tools or methods are, I mean, there's a bunch on the screen here, right? And so we've got things like, you know, a fault, an FTA, right? A fault tree analysis. Fault tree analysis is really done on the hardware level in particular, but can also be done at the system level, which is basically an inductive approach where you say, okay, I've got a safety goal, right? A safety goal might be something like, I want to make sure that the vehicle doesn't have too much underbraking, i.e. when I press the brake pedal, I want to make sure that it actually brakes. And so you have that safety goal and you go through each layer of the system and you just try and figure out what's causing it. And so that's a fault tree analysis. Then we have one called an FMEA. Is anybody familiar with an FMEA? I think this one's more common to come up in university, at least for mechanical engineers. All right, so an FMEA is failure modes and effects analysis. And so this is sort of the opposite of the FTA, where you start out and you go through everything that could go wrong in the system and you say, what's the impact of it? So you have a micro switch failure, or you have a wheel speed vehicle sensor, or a wheel speed sensor failure or something like that. And you trace it back up and you say, okay, what's the effect of that on my system? Is it going to cause any major issues? And then there's a bunch of these other kinds of methods for analysis, and we're not going to get into each of them because that's not really the point. But the point is to understand that there are a lot of these methods that have been developed by independent organizations. And so what happens is these methods are actually integrated. Basically, the best ones and the way to do it is turned into this process framework. And that's what the standard ISO 26262 is actually built on. And so what I want to cover in this section for what we have now is basically, what does ISO 26262 cover, and how does it actually help? Because we have all these tools and everybody kind of had their own process. So why do we need a standard? And what does the standard actually accomplish for us when we go through the systems today? And also, what are some of the gaps, right? Because we'll get to what do we need in the future. Obviously, if we need something in the future, then this isn't sufficient on its own for what we're trying to accomplish in the automotive world. Cool. So the motivation for all of this and why we need all these analyses and things like that is basically just because systems are more and more complicated today than they ever have been. And the complexity is increasing. And I'm sure a lot of you guys have probably heard something about, you know, the complexity comparison between an airplane, a modern airplane, and a modern road vehicle today. And the road vehicles are like way more complicated. There's a lot more systems involved, a lot more things can go wrong. And part of that is just because the environment is so much more chaotic. There's more vehicles on the road, they interact with each other. There's, you know, drivers are trained a lot less than in airplanes and things like that. And so we really need to make sure that we're checking all the bases. One of the main reasons that we try to standardize the kinds of work, the kinds of methods that we do to approach functional safety is because of this increase in complexity. And so the goal of standardization is actually to reduce complexity so that we can basically take on the problem in bite-sized chunks. You could call them units if you want, and ensure that we're actually finding all of the faults that are going to happen, that could happen, right? All of the potential failure modes, or all of the potential safety goal violations, or what have you. And so, you know, we look at, this is an example of a vehicle today. You know, there's a lot of different moving parts. You've got your basically user interface for the driver. You've got the actual drivetrain, right, which has a tremendous amount of automation in it now, right? It's not just like, oh, you have four wheels and you have a transmission, and when you press the gas pedal, it, you know, makes the car move. It's like, really now, even the gas pedal and the brake pedal and things like that are, they're placebo almost, right? Because what happens is when you press a pedal, or you put in an input to the vehicle, it actually just goes to a computer which processes what your intent is, and then tries to adjust the vehicle based on what the driver is intending to do. So it's not as simple as just, you press the pedal and it activates the brakes, or you press the pedal and it activates the accelerator. And this is how we have more and more advanced and complex features coming out that are things like your traction control, things like your automatic cruise control and such. Because all of the inputs by the driver are interpreted by the vehicle and then changed around and turned into whatever is going to make sense. Well, do you really want that much pressure on four wheels when you're braking on ice? It's like, maybe not. Do you really want that much? Do you really want to turn that hard, right? The computers even address understeering and oversteering concerns in vehicles today based on the stability algorithms. So all of this complexity means that it's really, really easy to miss things. If you guys have, I'm sure as you've kind of went through and you've started working on bigger and bigger projects in university, when you start out, it's like these really simple things that you can kind of think about it in your head and figure out where the problems are. And it's pretty straightforward, right? But once you start having bigger and bigger projects, then you start having to spend more time with, okay, how can I break this down into smaller chunks? How can I make sure that I'm actually building this up in a systematic way rather than just hoping it works? And the other thing that I'll offer is that a lot of the like modern vehicles, how we got to the level of safety that we have today is through trial and error, right? It is through, we build a vehicle and we put it on the road and it crashes, right? And right now it's really easy to point to, oh, well, the driver made a mistake, because the vehicles are largely in driver control, right? There are other features that could cause problems and things like that, but even those are pretty quickly overridden by driver input. If you're aggressive enough, even with the lane keep assist, for example, you can move outside the lines and change lanes. And so, or if you're, well, I guess automatic cruise control is a bad example, but if you put any input in, it's going to override what the cruise control is doing. And so I think the only ones that really aren't like that is like automatic emergency braking, for example. That isn't like that. Driver can't override those inputs. But right now it's easy to point to, okay, the driver made a mistake and the liability is clear. But as soon as you take away all that control for the driver, you start having other issues. So trial and error becomes harder when liability is less clear, because the companies take on a lot more risk for the vehicle as well. So in the midst of all of this complexity, let's talk a little bit about what the standard actually does. So we talked about the motivation for the standard. We talked about the complexity of modern vehicles. So let's talk a little bit about the details of this standard. So ISO 26262 actually defines and at any point here, feel free to cut me off, ask questions, of course. But it basically defines a process, and there's, what you see on your screen is just a standard prototypical V model is what we call it. It's called that because it looks like a V, really complicated. And basically the left side is all focused on design, and the right side is all focused on verification. So can someone take a shot at what verification is for? Why do we do verification and not just rely on designing correctly? Or what is verification?
As far as I've learned in engineering classes, verification is when you make sure that your final product meets all of your internal requirements. Perfect.
That's exactly right. And really, there's a couple ways that we do that, right? Some of them are through analyses, but the main one, frankly, is testing, right? And so when you guys go and you're developing your project over the next 40 hours, which is a long time, surprisingly short amount of time, but long time to be awake. Along the way, you guys are going to have to do some level of verification, right? Because you've got to make sure that it works, right? You don't want to get to the end, think you have this really rock solid design, realize you missed one or two things and it doesn't work the way that you expected to, or it has a couple critical faults that if the user clicks one button, they can crash the whole program, right? And so that's basically the intent of how ISO 26262 has this sorry, I'm gesturing on the wrong monitor with my mouse, has this whole process set up. So right up at the top here, we have this thing called an item definition, which is really straightforward. It's just basically defining what the system is going to do, what it's going to include. And this is basically the features that are going to be included. Is it going to have automatic emergency braking? Is it going to have cruise control? Is it going to have this lane keep assist thing that Tejas was talking about? And it's going to define those and talk about the limits of what they're going to do and all those sorts of things. And we move our way down to basically different levels of requirements. So right at the top, ISO has this process for hazard and risk assessment, which goes through basically all of the conditions that can occur in the road. And there's a list, it's all standardized. It's not like people have to make them up. And basically says, okay, what are the problems that could come out of these situations, and how can we avoid them, right? And that turns into these safety goals of saying, okay, let's make sure that, you know, regardless of condition, that the vehicle isn't going to have underbraking or oversteer or, you know, whatever other things that could occur. And then those safety goals basically turn into functional safety requirements and a functional level architecture, which is really straightforward. Basically, at a high level, how does information pass? We do this thing at Invensity called a functional mode diagram, which is just all about you know, these different operating modes that you might have in a vehicle and how they relate. What's going to trigger you to transition between states? Really talking about degraded functionality in different situations. So ISO 26262 does a really great job of handling, okay, I'm trying to I'm trying to brake. I know that I'm going to need to stop the vehicle at some point because I'm driving 60 miles an hour down an icy road. One of my wheel speed sensors stopped working, or two of my wheel speed sensors stopped working. How can I adjust what my vehicle is trying to do and how I'm responding to the driver input to maximize the performance that I'm getting out of the vehicle, despite the fact that the vehicle isn't going to have all of the built-in features? And so that's really the idea, is to try and figure out your degradation pathways and things like that for features at this functional level. Then we get into the technical level, which jumps into really talking about signal pathways and things like that. It's just a little bit more detailed, but similar kind of ethos. And then eventually we get down to actually doing the hardware and software design and the various kinds of analyses that were on the earlier pages, right? Dependent fault analysis, the FMEA, FTA, all that kind of stuff. And so all this is specified in the standard, and the details on how you actually do the exercises aren't, but the way in which you do them and the way that they feed into each other is. And so that's why we call it a process framework rather than a specific process. And then basically the left side is each of those things, just like Sonali said, each of those things is basically vetted or tested against your requirements, and you make sure that it does what you want it to do. And that's this whole thing called safety verification. And at the end, the whole system or the whole vehicle test is system safety validation to make sure that it does what you want. So that's what we have today. And one of the things that we'll realize as we go through this is, while there is some, you know, it does think about things like software, it's really only focusing on faults that could occur within the system itself. So in the vehicle, if something happens in the vehicle, how does the vehicle respond to that condition? And what that means is, what it's missing is, how does the vehicle respond if the environment does something crazy? And so Tejas can talk a little bit more about what that means going forward.
Sure. So yeah, so James mentioned there's this ISO standard. We follow it. It's a bunch of work products. But what it perfectly fits in. I don't want you guys to think that this is like something brand new or like we're re-engineering anything. It's like somebody, there's a bunch of engineers that have been and continuously will be developing cars. And ISO is just this like kind of like icing. It's like a top layer where they work on certain work products in addition to what they do, which helps create this thing. So we kind of which helps create this like safety. So I think, Sonali, you asked, you know, since ISO standards aren't always enforceable, like how would you say the government government regulation kind of plays a role in this. So 2011 or 2012, the guy we report to, or our boss, or our office head here, Fabian, came to Detroit, and he was saying, hey, we want to do an ISO 26262 project, and he pitched it to a bunch of clients, and every single client's like, you guys are crazy, we're never going to implement this in the USA. And it was a known fact, and he's like, yeah, we're not going to do this. And in Germany, government has said in product development specific to automotive, ISO 262 needs to be followed. So can someone tell me who was the first person to claim the self-driving car? Or who was the first person to say, I have released an autopilot? Which car company? Evan, I think you might know this one.
I get the easy then, Tesla.
Tesla. So Tesla was able to release this product. And it was, I think I want to say 2011, 2012, before any of this regulation had kind of come in. So Elon Musk was able to say, hey, this is an autopilot, this is a self-driving car. We've done autopilot and we've released it. And boy, did they come into that market. And like, as you can see, they're killing it. Like everyone's buying Teslas. Right after they released that, there was a few big accidents. The decapitation accident, if you guys have heard of that one. There's a few smaller ones. The decapitation was the big one. There's one that just happened June 1st. You can YouTube it. Just type in Tesla Thailand or something like that. And these are all things that happened recently. But after Tesla released their first thing and that the decapitation thing happened, government said, okay, we now need to, they didn't say mandate, but we're going to strictly enforce ISO 26262. So now Ford will say to their suppliers, hey, we want you to follow this standard. And then the supplier will be like, okay, they need to follow this standard. So they'll tell their supplier, who will tell their supplier. So it's like a trickle down effect, but like that's kind of where it's happening. So that's ISO 26262. And as James mentioned, that's like, if anything, the system goes wrong. So then comes to what's next. We have 15 minutes and I don't want to like bore you guys with the details, but what I just want to talk about, because this is very much like your guys' topic. It's like algorithm based and stuff like that. So if you go to the next slide, James, you can see that, okay, a bunch of, when you have a self-driving car, you have camera vision, you have radar sensors, sometimes you have ultrasonic sensors, you have LiDAR on some of them, and all these things are processing huge amounts of data, right? You have, I don't know if you guys have ever worked with like a self-driving car, but you have a map component, you have a LiDAR component, you have a radar component, and everything is like cross-referencing and processing and making judgments and trying to make sure the car stays in its lane but maintains speed. I mean, it's insane. And I don't know if you guys caught on to when I said this, like in some of these self-driving cars, I can't necessarily name who, but they have like 5 individual stacks of computers, and it's so hot in there that they not only have like an air-cooled system and the windows are open, they also have like a water-cooled system to just keep the inside of that car cool. Not because it's hot outside or the car is heating up, it's just the computer power. That's how much computing power is going through this. So when it comes to all these like algorithms and things like that, obviously, like, you know, algorithms will make mistakes, your computer bugs, software bugs happen all the time. But there's, as James mentioned, there's a whole different level, right? There's a whole different level of things that could occur that's not up to the car, that's up to the environment. So this happens if anyone's from San Francisco. I've heard this a lot, and I've seen it myself. Somebody will see a self-driving car, or like if it's like a biker, he'll just slam on his brakes to see what happens. Or they'll stick their foot out in the middle of the road to see what happens, just to mess with the system. And these systems are tuned extremely high. And you can tell what's a self-driving car. I mean, there's a giant like circular thing on the top of them. That's the LiDAR. And they're tuned to a very sensitive range. So they'll stop, right? But that's not like, you know, that's not a mistake that the car is making or anything like that, right? It's just reacting to its surrounding. That's great. Now, say I'm like a great artist and I like paint the side of my leg the exact same color as a road. Right? If I paint my leg the exact same color as the road and like it just matches just perfectly with like the asphalt, what if I stick my foot out there, right? And camera vision doesn't catch it. That's where the second standard kind of comes in. So like this thing, it's called SOTIF. I think, James, if you go to slide 16, we can skip over this slide. Here's another example. Apparently this is in Germany. I've never seen it here, but I think if you guys see on like Instagram and like YouTube, there's like people that make these like super real life chalk drawings on concrete, and it like looks like a big hole or something like that. It's like very, very realistic. So in Germany, apparently they draw like where it's like kids crossing, we have like a sign. They actually draw a picture of a kid onto the road. Now, what if your camera vision recognizes that, categorizes that as a kid, and then slams on the automatic emergency brake? Which, I don't know if you've ever been in a car with automatic emergency brake. It'll stop, you'll jerk, somebody will rear end you. It's like it stops on a dime.
It's pretty painful.
It hurts, but it saves the kid's life, right? So SOTIF, which is this new standard, kind of figures out, okay, how do we cross-reference? How do we double-check? So maybe camera vision sees something, but we need to cross-reference this with radar, or we need to improve our reaction algorithms. Or we should cross-check with like a different sensor output, right? Like, or we need to have an infrared sensor. I mean, there's the varieties of things, the possibilities are kind of endless, but that's kind of what these problems create. And again, SOTIF is like a systematic standard. There's a whole process you follow, but it's very, very much tailored to what algorithms are doing. I'll give you another example. This is actually from one of my clients that I've been working with like currently. So I don't know if you guys have done like the whole up north thing here in Michigan, but I went up to like Mackinac Island one day, and I was driving, and there was and I kid you not, I can find the pictures on my iPhone somewhere, but there was a trailer with there's like a pickup with a trailer, and somebody had one of those, those like kid cars, like they look like somebody will make like a Mercedes or like something like that, but it's like a child's car. They go like 2 miles an hour, and like a child like maybe 3-4 years will drive it. They had that sitting in the trailer. And I was like, if I have like an old beat up car, but like I was like saying, if my car had a camera vision sensor and it was able to categorize and say that car is made to like appropriate dimensions, it categorizes that as like a actual car, like into oncoming traffic. My God, the camera vision would be so confused. It'd probably try to slam the brakes or like steer. If I have like emergency lane keeping, try to steer me out of the lane. God knows what it would have done. So these are all different things like SOTIF covers, like which are different environmental aspects. Again, similarly, if you go to slide 18, James, this as another layer that kind of adds on to your product development. The next slide. So this like James said, HARA, FSC, TSC, that's like the ISO stuff. This kind of comes a little bit before, so you like do a little bit of research, R&D. It's a systematic approach, but you do all this stuff before, kind of make your algorithm strong to begin with. Then you work on how to make your product pretty safe, and then you kind of develop and release your product. That's kind of how these things happen today. So skipping ahead, I think it's slide 21, James. This is kind of the let me make sure. Yeah. So this is where SAE. It's like I don't know the organization's name, but it's the organization that talks about automotive safety. They come up with like the levels of self-driving and stuff like that. So level 0 is like your average Joe car, nothing. Level 1, it has like a few features. We're talking about maybe a little bit of automatic braking, maybe lane keeping. So like what a Tesla falls under is like between level 2 and 3. I think it's right around level 3 is where a Tesla falls in. Level 4 is actually you are not driving, which means like you are sitting there and there's a driver steering wheel and like a gas pedal, but you are actually not doing anything. You don't have to keep your hands on the wheel. On a Tesla currently, you have to put your hands on the wheel. Level 5 is no steering wheel, no pedals, nothing. You cannot change the car's direction. So ISO 26262, what James mentioned, is that first blue block. That's what that covers. SOTIF, what I've been talking about, this like whole checking out the environment, that covers up to level 2. We can make the argument to level 3, what Tesla should be covering. UL 4600, which is this brand new standard, is like level 3 and 4 and onwards. And then there's this standard called 21434, that's like cybersecurity. That should be covered from 0 to 5. I mean, anything compromising like the integrity or the cybersecurity of a vehicle is very, very dangerous. So coming back to our big question, right? Like, why don't self-driving cars exist? Honestly, it is because these cars are not robust enough, and these corporations are not ready to say that, hey, we can say with this much confidence that this vehicle can go on. Believe me, the car works. I've sat in them. At Carnegie Mellon, they started Uber's whole self-driving thing. And when we used to go out and like go to the bars and stuff, we would request an Uber and they'd be like, hey, this is a free Uber. It's a self-driving car. And we're like, sweet, free Uber. And I would hit yes. Little did I know that that was like just like a toy. Like somebody had put a bunch of engineering stuff into it and I was sitting in like a very, very scary thing, but it worked fine. I mean, I've ridden in them multiple times then and I've ridden in them multiple times now, and it's only gotten better. No major accidents. I mean, I think Uber's statistic was like they have like one very serious accident and one ran red light. So it's working very, very fine. But the issue is as soon as they say release, right? As soon as thousands of people start requesting Ubers that are self-driving, things like that, that's when it becomes very dangerous. And this whole standardization of these processes and things like that aren't there to be like, oh, this is a checkbox. It's more so that like people can say that, okay, we actually think our product is kind of risk averse. So that's kind of our reasoning as to why these cars aren't there. This is kind of what we work on a day to day. That's like kind of what our James and I specifically our expertise has been. So I want you guys to ask me some questions. We have 5 minutes left. You can throw up our contact information if you ever have any questions in the future. But if anybody has any questions, even specific to software and algorithm, like that's my project. My entire project recently has just been algorithm based. Please let me know. We'd love to try to see if we can answer some things.
Yeah, and while we're doing that, I'm going to put a link in the chat. If you guys can fill this out, it's just a feedback form. Really, really straightforward. That would be wonderful. When we do these kinds of things, we like to get feedback so we can improve them and adjust scope and things like that as we go. So if you could take just a minute and do at least the basics, first 5 questions or just a quick rating scale, that would be really great. Thank you.
Any questions? Okay, since I have like 3 minutes, I'll quickly just add one more like story because I feel like you guys like the stories I'm saying. This whole SOTIF concept about like seeing how the environment reacts. So there's like June 1st, this happened. So I wasn't arguing, but we were like debating with a client saying, hey, you should use SOTIF. They're like, nah, we don't have the time for this. We don't have the engineers. I was saying, no, I think you should. They're like, nah. And we would just go back and forth. And I was working on a variety of things for them. But then June 1st, this whole Tesla thing happened. So in this video, you guys can YouTube it. The Tesla is going, and there's a human standing on the side of the road saying, stop. He's like waving his arms. And there's like a truck or like a car tipped over on its side. And this Tesla is in autopilot, or autopilot, as Elon Musk says. And essentially, he bases a lot of stuff off camera vision. So I assume the camera vision sees the lanes. It definitely saw the object, but was unable to categorize it. And it didn't do any kind of cross-reference, no radar, nothing like that. So everything functioned as it should. It did not categorize that object, and it plowed right through that car. I mean, the car was just rolled over on its side, but just because it was unable to categorize it, it was like, okay, we couldn't categorize this car. I'm gonna drive right through it. That's where like these things kind of come into play, right? Really analyzing scenarios and making sure your algorithm accounts for things that you just don't expect in your wildest dreams to happen. That's where this stuff happens. And we're not sitting in a room and just like brainstorming, oh, what if this happens? Oh, what if this happens? There's a whole standardized methodology to this. And the methodology is actually like pretty reliable because you can see how many different outcomes kind of come from that. But specific to automotive and specific to algorithm development, it actually makes your algorithm very, very robust. It's a strong way to like say, look, we've accounted for all these different things. If you put our car in any of these scenarios, it should be fine. Similarly, wherever you guys work, depending on what products you guys work on, there's going to be similar levels of robustness test. Whoops. So you're going to be trying to figure out exactly how to like make your software strong and make sure it doesn't mess up and there's not bugs. We kind of just tackled the automotive self-driving kind of aspect of that. Cool. 2 minutes. If you guys have any other questions, obviously you can text us or email us. If not, I think that's kind of it from our end.
Knowing what you know about self-driving cars, do you get scared about getting in one, like on the road? Or like, do you guys get scared when you see one on the road?
No.
Okay,
No.
I know what's going
Because
on.
what I'm saying is like they're very well engineered things.
Mhm.
The cost, I think the cost of one of those self-driving cars is like $650,000. Just imagine how high quality of like and this is not the car. This is just the technology on top of it. $650,000, right? Like they work very well as long as you're not dumb, and you're operating in a proper domain. It should be fine, right? So if for example in Pittsburgh, these cars have been testing nonstop. If I were to get on one of these cars from CMU to the airport, it's done that route hundreds and hundreds and hundreds of times. I probably won't be that scared. When it comes to like the Elon Musk kind of cars, like the ones that have like autopilot and stuff like that, I'm even less scared because technically the responsibility is still in my hands.
Mhm.
You see what I mean? If the driver wasn't passed out when that car was flipped over, well, hopefully he hit the brake, right? Like those cars are made so that the reliability is more in their hands. So Elon Musk, all the self-driving features that are coming out, I feel completely fine because you're still sitting in the driver's seat and you're holding the wheel. And I think it like bugs you like a few seconds. When it comes to fully self-driving cars, I can see there's a little bit of risk, but still, there's points where like you never know. But I mean, again, depending on your domain and things like that, usually you'll be fine. I've done it. I'm alive. And there's only like 5 or 6 big accidents, but if you guys ever have any questions or if you work in self-driving or if you're like working on any of these products, like screenshot us or add us on LinkedIn. That's perfectly fine. And I'd love to like kind of help you guys out. It's just it's an interesting topic and I don't think we're near the end yet. So you'll see this.
Yeah, there's a lot of game left to play, as they say.
Yeah.
Cool. Thank you, guys.
Thank you so much, guys.
Again, please fill out the survey if you could, and hopefully we'll see some of you soon.
Yep.
Good luck with your projects.
If you see my brother, give him a punch for me.
I will. Thank you so much, guys. Had a great time.
Okay. Thank you.
I'm going to go ahead and end the meeting now.
Cool.